Good morning everyone and welcome to the December webinar from the IEA Clean Coal Centre. These monthly webinars are based on our technical reports which are available on our website at www.iea-coal.org. Residents in our member countries and employees of sponsoring organisations can download the reports for free after a one-off registration. You can find more details on our website. So the webinar I'm presenting today is on water issues and wastewater treatment in coal-fired power plants. I'm going to begin by looking at the vulnerability of the power generation industry to constraints in water availability before discussing what power plant operators can do to reduce their dependence on freshwater sources. This includes the use of non-fresh water sources and the conservation of water within a power plant. These two topics have been covered in previous webinars. And an earlier webinar examined water availability and water policy in China and the USA. The report on which this webinar was based also covered India and South Africa. Finally, I'll look at the treatment and reuse of wastewater generated in a coal-fired power plant. Reusing the wastewater will also lower your freshwater consumption, and this is the subject of a new report that is now out in draft. The vulnerability of the power generation industry to constraints in water availability is widespread and growing. As you can see from this figure, significant areas of almost every continent are currently facing a high level of water stress. Well, the figure is taken from the World Resources Institute's Aqueduct Atlas, and they define water stress basically as the ratio of total withdrawals to total renewal supply in a given area. So a higher number means more water users are competing for limited supplies. And so the areas in red are the most stressed regions. Now, regions where water is scarce face obvious risks, but even areas with ample resources can experience constraints due to droughts, heat waves, seasonal variations and other factors. Last year, a number of power plants in India had to temporarily shut down due to a lack of water, and this included all 5 units at the 1600 megawatt Farakka coal-fired power plant in West Bengal. The number of power plants affected is likely to increase in the future, especially with the growing energy and water demand in many parts of the world, and this could have serious economic consequences. As I said, demand for water and energy are growing, and this is principally due to the rising population and economic growth. Population is growing at about 80 million people per year, and it's been projected to reach over 9 billion by 2050. And the majority of the population growth will be in the emerging and developing economies. So unless water demand and supply can be balanced, the world is going to face an increasingly severe deficit. And a 40% deficit by 2030 has been projected by the 2030 Water Resources Group. And this is in their business as usual scenario. Groundwater currently provides roughly 1/3 of global supply, but the rate of extraction is outpacing recharge rates. So an estimated 20% of the world's aquifers have already been overexploited. And the quality of water is also deteriorating in some regions. And with deterioration of wetlands, this has reduced the capacity of the ecosystems to purify the water. So, what can power plant operators do to reduce their dependence on fresh water? They can look for alternative non-fresh sources, which I've listed here. Most power plants on the coast are already using seawater for cooling purposes. But the economic feasibility of using these water sources will largely depend on the distance to the power plant, the amount of water available, its price, and the cost of treating it. So I'm just going to look at municipal wastewater as an example since this is the most used alternative water source for cooling towers. The other sources were discussed in a previous webinar which I gave in July last year, which of course you can still listen to. India has made it mandatory for power plants to use this wastewater source if it is available within a 100-kilometre radius. And the Chinese government has also recognised the importance of fully utilising its municipal wastewater resources. And their policy is that all new power plants will need to use this water source, that is, if it is available. Right, as you can see from the map, the majority of coal power plants in the USA, and these are the orange dots, are situated near to a publicly owned municipal wastewater treatment plant, and these are the blue dots. Therefore, many power plants could potentially use this water source. However, this is not an option in some countries such as South Africa. This is because most of the South African coal-fired power plants are not situated near the cities. So this will make this the municipal wastewater source rather than practical and expensive for them. So instead, the power plants could possibly use mine water since they are located near the coal mines. And of course, using mine water drainage also has the advantage of turning a water pollution liability into a water resource. Now, operational problems which have been associated with the use of municipal wastewater, such as corrosion, scaling and biofouling, can be controlled with adequate water treatment and by the addition of chemicals. And any human health concerns are the possible emission of bacteria and other trace contaminants in the aerosols emitted from the cooling towers. These can be minimised with proper control and the management of cooling operations. Right, another way of reducing dependency on fresh water is to conserve water within the power plant. And I've included this figure to show you the main places where water is lost and added in a power plant. The largest loss is from the cooling tower, where water is lost through evaporation and blowdown. Right, this figure gives an indication of the amount of water that is withdrawn and consumed in a power plant. It's for a 500 megawatt subcritical plant which is burning bituminous coal. The cooling system, which is a wet cooling tower, accounts for the largest usage of water. And this is followed by the FGD scrubber, which in this case is a wet limestone process. I'll be discussing the treatment of wastewater from these two systems later. Right, substantial water savings could be made by employing dry cooling, and this utilises air instead of water to condense the steam. For example, one power plant in South Africa that employs a direct dry-cooled system uses about 3.5 million cubic metres of water per year, and this compares to around 50 million cubic metres per year for an equivalent wet-cooled power plant. So of course this gives you a saving of around, well, over 46 million cubic metres a year, or if you prefer, 46 billion litres a year. Governments in several countries are promoting dry cooling as a means of conserving their water resources. In China, for example, new inland coal-fired power plants must be dry-cooled. And this policy is despite the drawbacks of dry cooling. And these drawbacks include a lower power efficiency, higher operating costs, and a larger footprint than the equivalent wet-cooled plant. Overall, the power efficiency is lowered by about 2 to 7 percentage points, although this can be even higher on hot days. And this because air is a less efficient cooling medium than coal. Because lower efficiency means more coal is needed per unit of electricity, and this in turn can lead to higher CO2 emissions. Well, a lot of research is being done to diminish the disadvantages of dry cooling. For example, there are 2 research development programs in the USA that are specifically targeting dry cooling, and I've listed them on the slide here. In addition, if you build more efficient power plants, this can save water. both supercritical and ultra-supercritical power plants use some 15 to 20% less water than subcritical plants, because there's a policy in a number of countries that all new coal-fired power plants must be supercritical or ultra-supercritical, so this will have the added benefit of conserving water resources. Right, moving on to wastewater. This figure shows the main sources of wastewater which are generated at a power plant, and they include wastewater from the steam system. This is such as your boiler blowdown, and wastewater from the treatment of the boiler feed water and condensate polishing. Power plants with a once-through cooling system return the cooling water to the water body at a higher temperature, and the resulting temperature rise in the receiving water body is often regulated. For example, India limits the temperature to no more than 10 degrees centigrade higher than the intake water temperature. And power plants with recirculating cooling systems generate a waste stream from the periodic blowdown of the cooling tower. Both the once-through discharge and the cooling tower blowdown can contain pollutants resulting from the erosion and corrosion of piping and the condenser, and from chemicals added to prevent corrosion, scaling and biofouling. And as I said, I'll be discussing the treatment of the cooling tower blowdown later. Handling the bottom ash and or the fly ash in a wet system can generate wastewater. Of course, fly ash is usually handled dry when you're going to sell it for cement or concrete manufacture or for other uses. Wet bottom ash and fly ash may be transported and stored together or in separate ash impoundments, and other waste streams may also be sent to the impoundment. Of course, overflow from the impoundment can be recirculated back to the power plant for reuse or treated and discharged. Other wastewater streams from ash management are surface runoff and leachates from dry ash landfills, which I don't show in this figure. Of course, the leachates result from rainwater or water added to control dust percolating through the ash and any other deposited waste solids, such as FGD waste. So the composition of the wastewater stream will depend on what is stored in the landfill. Another wastewater stream, which is shown in this figure, comes from the wet scrubbing systems. And this is used, of course, the scrubbing system used to control your sulfur dioxide emissions. I'll be discussing this treatment later. And other sources include runoff from the coal stockpiles and wastewater from the cleaning and washing of equipment, such as boilers, air heaters and electrostatic precipitators. And there's also sanitary water and wastewater from on-site laboratories, from general site cleaning and surface runoff. The volume, flow rate and characteristics of all these various wastewater streams will depend on the individual plant. Streams with similar composition are commonly combined before treatment, whereas others, such as FGD wastewater, may be treated separately. The treatment of the various wastewater streams commonly involves a number of sequential steps, and these can include physical, chemical, physiochemical and biological processes. Physical technologies are used to treat wastewater streams which contain a high amount of suspended solids, and these solids can be removed by screening, sedimentation and or filtration. Chemical treatments include neutralization, pH control and precipitation to remove the dissolved solids. And biological processes involve the use of bacteria to degrade the dissolved organic substances. The choice of technologies to treat a particular stream depends on a number of factors, some of which I've listed here. Of course, the choice will, of course, be site-specific. One of the reasons for treating wastewater, which is the last point in the list here, is to meet your statutory regulations. And these regulations can take different forms. Most countries have regulations on the quality of their surface, ground and coastal waters, and these will limit the amount of pollutants that could be discharged into them. Some countries have national regulations limiting the amount of pollutants that can be emitted in effluents from industry, and these of course will cover power plants. But there are only a few countries which have set limits explicitly for discharges from coal-fired power plants. In addition, power plants must obtain a licence or permit before they can operate, and these can contain restrictions on liquid discharges. And these limits may be stricter than the national regulations for power plants or industrial effluents, and may include additional pollutants. So in the report I looked at legislation in 8 countries in the European Union, and the countries are among the top 12 countries in the world that consume steamed coal. However, the regulations are not always adhered to, and the level of monitoring and enforcement will have an important effect on the achievement of cleaner rivers and water bodies. Right, this table shows the limits which are specifically for cooling water discharges from coal-fired power plants. These are stipulated in India, Indonesia and the USA. As I mentioned earlier, wastewater from the cooling system is typically the largest source of wastewater at a wet-cooled power plant. Actually, the countries here regulate different contaminants. All 3 of them include limits for chlorine. But as well as constituents listed here, the US standard also stipulates that there should be no detectable amounts for another 124 priority pollutants. And these include other heavy metals such as arsenic and mercury. Right, I've included this table to give you some idea of the composition of cooling tower blowdown and the range in the amount of pollutants that can be present. I've only included some selected parameters. The figures are taken from an old survey of power plants in the USA and may not be representative of power plants today. For example, chromate-based treatment for cooling water is not often used nowadays. The composition and quantity of blowdown does vary greatly from plant to plant, as it mainly depends on the make-up water. For example, whether you're using surface water, municipal wastewater or another source. And of course on the chemicals added to prevent fouling, scaling and corrosion. As you see, for some plants, zinc and phosphates at least will need to be removed to meet the limits stipulated for cooling tower blowdown, which I showed you in the previous slide. I've included these limits in the column on the right. Of course, some of the constituents classified as priority pollutants, such as copper, mercury, and these were specified in the USA, may need to be removed since they don't allow any detectable amounts for these contaminants. Right, so some blowdown may have a high enough quality to be used elsewhere in the power plant without any treatment. For example, you may be able to use it for bottom ash quenching and transport. Otherwise, some of the technologies that could be used to treat the blowdown before it is discharged or reused are listed here. The wastewater can be sent to an evaporation pond, but this does mean that water that could be recovered for reuse is lost to the atmosphere. A vapour compression evaporation system that uses a falling film evaporator can be employed. These are commonly known as brine concentrators. And I've shown one design here in the figure. Up to about 95% of clean water can be recovered for reuse as boiler makeup or for other uses. But you do generate a concentrated wastewater stream, which is called the waste brine. This waste could be sent to a crystallisation unit to recover some more water and to generate a solid waste product that could be landfilled, or in some cases, it may be possible to sell it. So this in effect creates a zero liquid discharge system for cooling tower blowdown. Water-stressed countries such as China have already introduced policies requiring power plants in certain areas to become zero liquid discharge. So power plants will increasingly going to be forced to treat and reuse all of their wastewater streams. Right, now one power plant that's using a reverse osmosis system to treat the cooling tower blowdown is the INDIANTOWN coal-fired cogeneration plant in the USA. This power plant replaced its two brine concentrators with a two-pass reverse osmosis system. The blowdown first passes through the microfiltration unit, which is labelled MF in the figure, and this removes the suspended solids. And then the dissolved solids are then removed in the reverse osmosis system. The final step is a polishing stage in a mixed bed demineralizer, and this provides water of a high enough quality that can be used in the boiler feed water systems, as boilers require water with a very high purity. The rejects from the reverse osmosis and the microfiltration units are processed in the spray dryer absorber, which is used to reduce your SOx emissions, or it is used for lime slaking for use in the absorber. So the plant has therefore managed to maintain its zero liquid discharge status. And using a reverse osmosis system also gave it the flexibility to use different combinations of make-up water for the cooling tower. It's named water from the nearby creek, municipal wastewater, and some highly saline groundwater from the wells. And eliminating the brine concentrators has resulted in a reduction of the parasitic power consumption. Right, I'm now going to look at flue gas wastewater. So scrubbing systems are employed to control sulfur dioxide emissions from coal-fired power plants. This is in order to meet the air quality requirements. Wet scrubbing is the most common system in use, and it has over about 80% in the installed capacity worldwide. Of course, when you use it, large volumes of wastewater are generated. So this table gives the discharge limits for wastewater from wet FGD systems, which is stipulated by the European Union, China, and the USA. The US limits are from the new 215 emission limitation guidelines, which are currently under review. The parameters are in milligrams per litres, except for pH. As you see, the limits for mercury and cadmium in particular are strict. The composition of wastewater from wet limestone FGD plant is indicated here. Of course, only some selected parameters are given. It is for the dry-cooled Kusile power plant in South Africa. It shows that most constituents will exceed the discharge limits, particularly the heavy metals. The discharge limits I've shown in the table actually just give the range which was set by the three countries in the previous slide. Wastewater from the FGD system is typically the most difficult stream to treat in power plants. So some of the techniques used are listed here. The use of surface impoundments, which are also known as settling ponds, is a common method in the USA. However, you must design the impoundments to prevent leachates from polluting the groundwater. And these systems remove suspended solids and metals which are in the particulate phase by gravity, but of course it doesn't remove the dissolved metals. Wastewater can be mixed with fly ash to form a high solid paste that resembles toothpaste. This is the option, the last option listed in this here. Now the paste can be piped to a nearby disposal site, which is deposited and allowed to desiccate to form a solid mass before another layer is added. So this locks away the constituents which could be of concern in both the fly ash and the FGD wastewater. Of course, the mine-mouth power plant will have the option of pumping the paste to the underground mine and beneficially use it for black filling. Right, the discharge limits set by the European Union and the 215 emission limitation guidelines in the USA are based on limits achievable with best available techniques, or BAT. In the USA, the BAT technologies are chemical precipitation followed by biological treatment for existing power plants. And for new power plants, the technique is evaporation. So a chemical precipitation scheme I've shown in this figure, and this involves pH adjustment, coagulation, flocculation, precipitation, clarification and filtration to remove the dissolved and suspended solids. And of course you can also add polymers to enhance the removal of heavy metals such as mercury. Biological systems use microorganisms to basically transform soluble pollutants into a solid product. And this can be accomplished using bioreactors or constructed wetlands. And of course you choose your microorganism to remove what is your targeted pollutant. There are various designs of bioreactors, and these can include fixed film and suspended growth bioreactors. The fixed film design is used at 2 power plants in the USA to remove pollutants such as mercury, selenium, arsenic and zinc. The FGD wastewater does require some pre-treatment before it enters the bioreactors. This is commonly known as like chemical treatment. But the microorganisms are sensitive to changes in the temperature and composition of the wastewater. You need a constant flow rate is preferred, otherwise the treatment efficiency is reduced. A constructed wetland system is an artificial wetland, and it uses a combination of natural and physical absorption processes to reduce the concentration of organic and heavy metal pollutants. However, it does require a large area of land and a long residence time, usually several days. Thermal evaporation systems include crystallization, flue gas, duct evaporation and spray dryers. Brine concentrators followed by crystallization of the brine reject is employed at 5 coal-fired power plants in Italy. I discussed brine concentrators earlier. Here the Italian power plants use the clean distillate from the brine concentrator and the crystallizer as make-up water for the FGD scrubbers and cooling towers. And the salt cake residue from the crystallizer is sent to landfill. All of the power plants are zero discharge plants, so no wastewater is discharged. So consequently, there are no discharge limits to meet. And of course, they also avoid all the associated monitoring and measuring requirements. Several power plants in Europe and Asia are evaporating FGD wastewater in the flue gas duct. This technique does not require any chemical treatment. The wastewater is sprayed directly into the duct downstream of the air heater, which is evaporated by the heat in the flue gas. So the resultant solids are then removed with the fly ash in the downstream electrostatic precipitator or fabric filter. Of course, the amount of water that can be handled is limited by the amount of flue gas available and the need to maintain the minimum temperature required for the ESP or fabric filter operation. It also needs a relatively long flue gas stack to evaporate all of the wastewater. In addition, the residues will contaminate the fly ash, which could make the fly ash unsaleable. The FG wastewater could be sent to a spray dryer. This uses the heat from the slipstream of the hot flue gas to evaporate the wastewater. The slipstream is taken from upstream the air heater, which is the APH in the figure, and WSD is the spray dryer. The evaporated water and solids can be returned to the duct downstream of the air heater, and then of course the solids are collected with the fly ash in the ESP or fabric filter. But this will again contaminate the fly ash, which could make it unsaleable. So to avoid this, you could install a separate fabric filter to collect the solids and any fly ash present in the flue gas which is exiting the spray dryer. Both reverse and forward osmosis systems have been installed at power plants to treat FGD wastewater. So the first commercial application of a forward osmosis-based zero liquid discharge system was at the 1.3 gigawatt ultra-cyclical CHANGXING power plant in China. Here it is used to treat the reverse osmosis reject. The forward osmosis system is called ClearFlow MBC in the figure. It consists of 3 parallel trains which are supported by a single draw solution. And this configuration allows the system to handle a flow rate of 30 to 110% of the design flow. And it also, this is all whilst it continues to provide a consistent feed quality to the final crystallization step. The clean water is combined with the pre-treated FGD wastewater and passes back through the reverse osmosis system. And the clean water from the reverse osmosis and crystallization units is reused as boiler makeup. Up to about 10,000 tonnes of dried salts are recovered per year by the crystallization, and it's sold to the local chemical industry. A test of this forward osmosis system at the Water Research Centre in the USA on FGD wastewater found that it could meet the US emission limitations guidelines for arsenic, selenium, mercury and nitrates. So, what are the key messages I want to leave you with? Water availability is becoming an important issue for coal-fired power plants and will become more so in the future. The various national or state governments are likely to introduce more regulatory restraints on its usage. Consequently, power plants will need to look for alternative non-freshwater sources, retrofit water-saving technologies, and/or treat and reuse the generated wastewater. Limits on the quality of the wastewater discharge could become stricter in some countries, with growing environmental and health concerns over the quality of surface and coastal water, and also, of course, with increasing concerns over the availability of fresh water. So both the EU and the USA have recently updated their discharge limits for wastewater from FGD systems. Water policies in countries such as China are forcing power plants to become zero liquid discharge as a way of conserving water resources. So this will eliminate the need to meet the discharge limits and also the associated monitoring and measurement requirements. Using waste streams within a power plant will reduce the amount of wastewater that needs to be treated and the volume discharged. It also lowers freshwater consumption, and this is becoming an increasingly attractive economic procedure, particularly in arid regions. So, thank you for listening. I'll just see if there are any questions. But while we're waiting, I have to say that the presentation will be available for download later this week from the webinar page of our website. And if you do think of any questions, you can always email me at the address shown here, and I'll do my best to answer them. Right, I've just got one which says that you mentioned that you cover legislation for several countries in your plant. So what are the countries you cover? Right, yes, if I can remember them all. It includes the USA, Indonesia, India, China, South Korea, South Africa, Australia and Japan, and of course the EU. Of course, say that in the reports that where countries don't actually have discharge limits specifically for power plants, I just quote the general water quality standards. But I have tried in these cases to include an example of a power plant, a permit from the power plant, just to give you some idea of the discharge limits that apply. Another one says, could you please mention recent reference documents for the best available techniques for large combustion plant water consumption matters, e.g. the UF breeze? Did your institution release such types of report? We don't actually release them, but the EU BREF forum, which I took the FGD waste limits from, was published in July, I think it was, this year, in the official gazette for the European Union. The draft report is available from there's a website. You can download it. I'll certainly give it in my report, the web address. But if you can't find it, if you email me, I'll send you the link. Number 6, you mentioned the use of dry cooling increased the carbon footprint. Have you quantified that? No, I'm afraid I haven't. Are there water savings from using a Healy coal plant compared to a subcritical plant? That is, from more efficient boiler and emission control systems. Well, there certainly are if you're using supercritical and ultra supercritical compared to subcritical. I said you could save between 10 to 20%. But if you're installing emission control systems, then that will use water. But as I've said, I've talked you through some of the ways you can then save water from the Healy plant. Right, well, that don't seem to be any more questions coming in, so I'd just like to say that the next webinar will be on the 24th of January next year, and will be on the supply chain costs of biomass for co-firing. And presenters will be Ben Dooley and Patrick Mason. So thank you for listening, and goodbye.